Hello, in this short video, we'll discuss the files you'll use during the CONVERGE workflow. The CONVERGE workflow is divided into 4 main stages. The CAD import and cleanup, where you prepare your geometry for the ACFD simulation. Case setup, where you define your case with input and data files, the simulation itself. And post-processing, where you'll visualize the simulation outputs. As shown on the image on the screen, each stage will either require files as an input or will generate files as an output. Understanding the role of each file and the information it contains will help you efficiently set up and post-process your case. It will also help you troubleshoot any errors you may get when running your simulation. In the rest of the video, we'll go over each stage in the CONVERGE workflow and the files that are associated with them. With that said, let's get into the first stage, CAD import and cleanup. In this stage, you will be mainly working with CAD files and surface files. Typically, you'll import a CAD file, clean up and prepare the geometry, and then convert it to a surface geometry file, which we will then work with throughout the case setup. The surface geometry information must be contained in a .dat or .cgns file. To see what type of CAD files you can import into CONVERGE, go to Import CAD in the File drop-down menu. And then, once the CAD model import panel is open, click on the Supported Formats button, and this will bring up a document that lists all the CAD file types you can import and export. You can also import your surface geometry directly if you have a .dat or .cgns file. The next stage is the case setup. This is where you'll prepare all of your input and data files that you will need in your case directory to run the simulation. The input files, which are denoted by the .in suffix, contain numerical inputs, model parameters, and boundary and initial conditions. Most CONVERGE input files use the YAML format, a human-readable data serialization language that organizes parameters into clear settings blocks. There are quite a few different input files. Some are required for every simulation, such as inputs.in, boundary.in, initialization.in, stream settings.in, and solver.in. While others are only required when you are using a specific feature, such as fsi.in when FSI modeling is active, or turbulence.in when turbulence modeling is active. Let's take a look at some examples. The first example we'll look at is inputs.in. This file is the master controller for your simulation. It dictates solver settings, which physical models are active, simulation timing, and many other settings. I want you to take note how for each setting, there is a brief description included. Next, here's the turbulence.in file. It contains information such as the turbulence model you're using and its parameters. It also contains information such as coefficients for all of the turbulence models. All input files can be edited directly in the file, but we recommend that you set up the case in CONVERGE Studio and then export the files to avoid any unintended errors. The other type of file you have to deal with here are the data files, which are denoted by the .dat suffix. The data files used in CONVERGE can contain thermodynamic properties, chemical reaction data, and surface geometry information. For example, in the last stage of the CONVERGE workflow, you were introduced to the surface.dat file, which contains the triangulated surface geometry. Other examples of data files you may use include mech.dat, therm.dat, and transport.dat, which are commonly used with combustion simulations. Specifically, mech.dat lists all of the elements and species used in the simulation along with their reactions. Therm.dat contains the thermodynamic information for each gas species, and transport.dat contains molecular transport properties of gas species. Once your case is set up, you'll need to export the input and data files to your case directory in order to run your simulation. To export these files, click the Export Input Files button in the main toolbar, then specify the files you want to export and the directory you want to export them to. Before exporting your input files to your case directory, It is a good practice to perform a final validation in Studio. With the final validation, CONVERGE Studio performs validation routines on the parameters you specified in the case setup doc. Additionally, it validates the geometry to ensure none of the errors that prevent CONVERGE from running are present. Another method you can use to check your inputs for errors is the check inputs utility. By running the check inputs utility, you can verify your settings without checking out a license. The solver will flag any errors in your YAML structure or physical parameters before the simulation starts. Additionally, when using the check inputs utility, CONVERGE will write some files that we'll discuss later in more detail, such as the screen output log file, the converge.log file, echo files, and the active variables log. Once there are no errors, you are ready to run your simulation. Once the simulation is running, CONVERGE provides real-time feedback through two main channels: screen output and the log file. First, the screen output gives you a high-level view of the simulation's progress, showing the current time step, cycle number, and various status updates. CONVERGE writes simulation status reports to the screen output as it reads the input and data files, sets up the mesh, encounters situations in which a warning is justified, and as it writes output and restart files. The screen output generally prints to the terminal. However, you can optionally redirect the screen output to a text file, such as log.out, by adding the following extension after the converge run command. Now let's take a quick look at an example of the screen output. As we scroll through, we can see it reading the input files, performing load balance, giving warnings, and writing or post and restart files. And then we get to the meat of the screen output, where for each time step, it'll print the percentage of the simulation that's been completed, the current simulation time, and the time step with the time step growth limiter. Next, the log file, or converge.log, is the black box of your simulation. It contains detailed iteration data, convergence information, timing statistics for every processor rank, and many more details about your simulation. The level of detail available in the log file is determined by you. To change the level of detail, go to the Run Parameters panel, the Miscellaneous tab, and then you can select from the screen print level. Your options are concise, intermediate, verbose, and more verbose. For example, verbose adds info about the step-by-step convergence of the iterative algorithm, as well as final convergence of turbulence, species, and passives. While more verbose adds information about convergence information within each loop of the iterative algorithm, including additional information about solving detailed chemistry and where in the simulation domain the recovery or time step limitation happens. It also includes timing information, such as the total computational time for a cycle, and the time taken by other major parts of the solution process, such as load balancing and solving the transport equations. It is important to note that the log file output is buffered, so if the simulation terminates abnormally, some portions of the log may not be written. That covers the two main logs you will refer to while monitoring your simulation. However, there are other specialized logs that you should be aware of. The first special log we will cover is the MPI_latency.log. The MPI latency log is useful for diagnosing network delays on high-performance computing clusters and is only written for Linux simulations performed on a cluster. At the beginning of the simulation, CONVERGE calculates a representative network latency between rank 0 and every other rank. It then writes the minimum, maximum, and average latency to the screen output and writes each rank's latency to the MPI latency.log. You can perform a latency check and get the MPI latency.log without actually running a simulation by passing the check system argument at the command line. Next, the active variables log provides a complete directory of every variable available in your specific simulation for AMR, post-processing, mapping, restarts, and UDFs. It also tells you what variables are transported during the simulation. As a reminder, you can get this file by using the check inputs utility. Now let's take a look at an example. For each variable, you can see its availability and its type. The type refers to its data type, which is useful for writing UDFs, and the availability is given as a series of letters. Each letter represents one of the categories for which the variable can be available. For example, the aspect ratio variable is available for AMR, post-processing, and UDFs. The last specialized log we'll cover is the error log. It provides a detailed stack trace to help technical support identify the failure point. When a simulation fails, Converge will write a detailed stack to convergence_error_rank number.log, where the number indicates the processor rank on which the errors occurred. Another type of file that may be helpful to troubleshoot the simulation is the echo file. There is an echo file written for each input file in the same directory, and it is the exact copy of the corresponding input file. The echo file gives you the ability to review the input parameters and identify problems with the case setup. For example, if a particular input file contains a parameter that does not appear in the corresponding echo file, the parameter must have been formatted incorrectly and thus Converge could not read it. As the solver runs, in addition to writing the log files already discussed, it writes various output, restart, and map files that will be used in the last stage of the Converge workflow. Possibly the most important files Converge writes during the simulation are the output files, which contain the results of the simulation. Converge provides two different types of output, cell_average.out files and cell_by_cell.h5 files. These files allow you to analyze and visualize the results of your simulation. First, the cell_average_data.out files are ASCII formatted output files that contain spatially averaged data for the entire domain or individual regions. These are updated at a user-defined frequency and are perfect for plotting pressure traces or mass balances. Some examples of .out files include thermo.out, which contains information such as the average pressure, temperature, and heat release rate, and the turbulence.out, which contains information such as the average TKE, turbulent dynamic viscosity, and turbulent kinetic viscosity. The types of .out files generated depend on the type of simulations you are running and the models that are activated. For example, if you are running a simulation in which gas emissions modeling is activated, Converge will generate an emissions.out file. Let's take a quick look at an example. This is a thermo.out file. Each column represents a different variable, and each row represents a single time step or cycle. As mentioned earlier, the frequency at which Converge writes data to the output files is determined by the user. To specify the frequency, open the Output Files panel, and then go to the Writing Time Intervals tab. You will then specify the frequency in the time interval for writing text output field. Lastly, you can easily plot the data from any .out file in the line plotting module, which you can get to on the bottom left side of the screen. Next, cell-by-cell post.h files contain individual cell quantities for all cells in the domain. Unlike the .out files, the binary .h5 files cannot be read by a human and are meant to be viewed in post-processing software like TechPlot, ParaView, GMC, EnSite, and FieldView. There's a lot of information that we can include in these files, and like all things in CFD, there is a trade-off involved. Including too much information in the output can take up a lot of memory and slow down the simulation, but not including enough information can affect your ability to analyze the results. To determine what variables you want to include in the post files, open the Post Variable Selection panel. Here, you can select which variables you want to include. Additionally, for multi-stream simulations, you can combine the data for all streams into a single set of post files. Write a separate set of post files for each stream, or write separate sets of post files for steady state and transient streams. That covers the output files Converge creates. Next, we'll move on to discussing restart and map files, which help you initialize your next simulation. Restart files are snapshots of the simulation state. They include all the information you need to restart your simulation from that point in time. For example, If your run is interrupted or you need to extend the end time, you can restart exactly from where you left off. The number of restart files written and the frequency at which they are written are determined by the user. To do this, open the Output Files panel, go to the Writing Times Interval tab, and the two settings we are interested in here are time interval for writing restart output here, and maximum number of restart files saved here. For example, as it's currently set up, CONVERGE will write a restart file every 10 seconds and only keep a maximum of 3 restart files. If the simulation runs long enough that more than 3 restart files are written, CONVERGE will get rid of the oldest restart files when writing the next one. So, if the simulation runs for 99 seconds and writes restart files every 10 seconds, the restart files you'll have at the end of the simulation will represent the simulation at 70, 80, and 90 seconds. Map files, on the other hand, allow you to initialize a new simulation with data from a previous run. For example, you can map the results of a cold flow run to initialize a combustion case. Map files are automatically written at the end of the simulation. However, you can also specify CONVERGE to write them at other times as well. To specify the times at which you want CONVERGE to generate map files, open the Output Files panel, and go to the Writing Time Intervals tab, then mark the checkbox next to Generate Map Files, then click on the glasses icon to specify the times at which you want the map files written. If nothing is configured here, then CONVERGE will only write a map file at the end of the simulation. There are a couple of different map files you may run to. The map file you encounter most is the map.h5 file. This contains the mapping data for the stream it is associated with. This map file is generated for all simulations. And if your simulation is using parcels, then you will also see a map_parcel.h5 file, which includes mapping information for parcels. Lastly, if your simulation includes inflow, outflow, or flow-through interface boundaries, CONVERGE will also generate a map_bound.out file for each inflow, outflow, or interface boundary. These contain information about the cells attached to the corresponding boundary, used to specify boundary conditions for your next simulation. Now that we have gone over all the files CONVERGE writes during and at the end of your simulation, let's look at where to find them in your case directory. At the highest level, you will find all of your input and data files as well as the echo files. You may also find your screen output log file if you choose to redirect the screen output to a file. Here, you will also find a folder containing all of your output files. Every case will have at least one folder titled outputs_original. In some cases, it may have additional output folders if you ran the simulation from a restart file. In that case, they'd be called output_restart with a number at the end corresponding to the restart file number. Now let's go one layer deeper and check out the outputs original folder. Here you'll find several of the files we discussed earlier, such as the active variables log and the converge.log. There are also some .out files like memory usage.out and cell count ranks.out that apply to the whole domain. This is also where you'll find any restart files. Aside from the individual files, you'll also find a couple of folders. One is called output, and it contains all of the post.h5 files from your simulation. And the other, or others, are named after the streams they represent. So if you only have one stream, you'll only have one folder called stream 0. And if you have multiple streams, you'll have other folders titled stream 1, stream 2, and so on. In the stream folders is where you'll find stream-specific map files and the .out files that are averaged over the whole stream or averaged over regions within that stream. If the stream contains multiple regions, CONVERGE writes files that are averaged over the stream as well as files that are averaged over each region. And depending on your specific setup, you may also see additional files or folders not explicitly covered in this video. And the image on the screen summarizes the case directory structure. Just like you can check the input files without running a full simulation, you can also check your output files with the check outputs utility. With this utility, CONVERGE validates the mesh and confirms which output files will be produced by the current case setup without running the full simulation. The final step is visualization. As we previously went over, CONVERGE writes individual cell data into binary post.h5 files. These files contain the full 3D state of the domain, but require conversion for most post-processors. Using the post-convert utility, you can transform these files into the appropriate format for a variety of post-processors like TechPlot, EnSite, FieldView, and ParaView. Additionally, if you have many streams, you can choose to combine them into one file or keep them separate to focus on a specific fluid or solid region. To convert your post files, go to the Post-Processing 3D module, and then give your case a name and specify the file type you want to convert to, and then specify your output directory. From there, you'll need to specify the files you want to convert and which cell variables you want to convert. Depending on the information included in your post files, you may also have to select liquid parcel and solid parcel variables that you want to convert as well. Once you've made your selections, click Convert, and then your converted files will be saved in the same output folder as the post files you converted. Now, you can use those files in the post-processing software of your choice to visualize the simulation results. Mastering the file structure of CONVERGE is about more than just organization. It's about having full control over your simulation. From the structured YML of your input files to the robust binary data of your output, every file plays a role in delivering accurate CFD results. That brings us to the end of this video. For more details, refer to the in-depth training materials and documentation available on the CONVERGE Hub.